Today we're going to get into nonlinear control, finally. And if I was looking at a scalar system, I just have x dot equals f of x plus gu. Let's make it easy and make g greater than 0 a constant. Doesn't have to be, but that makes it kind of easy. And this is what we call a nonlinear system in a affine form. So we have like f of x over here and g times u over here, and they're kind of separated. We don't have like an f of x and u. So if you see something like that's f of x and u, where x and u is kind of mixed in together, that's in non-affine form, that's more difficult to deal with. Basically impossible. You essentially want to convert it, even if it's in non-affine form, you want to kind of convert it into this form, or have some approximation of it in this form before you can really deal with it with the methods in this course. So, I mean, I guess the simplest thing to try would be u equals minus f of x over g minus 1 over g kx. And then x dot equals negative kx, where k is a positive constant control gain, is what kind of system? What do I get there?
Optimal.
Sorry?
Optimal.
Well, not necessarily optimal, but getting close. How do you describe that system? What does the solution look like? Exponential? When you say exponential, I think increasing.
Exponentially decreasing.
Yeah. Negative exponential? That's
Yeah.
what, yeah. So like, this is like, you know, if you remember your linear systems, this is about all you have to know from your linear systems course. This is what you do have to know. That's an exponentially stable system. If you calculated the solution to that, it would be x of t equals e to the negative at, right? Everyone remember that? So negative e to the negative at is exponentially decreasing function. So exponentially stable. So that's kind of the goal. Is you kind of want to see systems that look like this. That's perfect. So we took out these nonlinearities by canceling them out, and we end up with this best possible case scenario. Stable, exponentially stable linear system. So it's kind of a nice result. Trouble is, the idea that you would know f and g in a nonlinear system is a little unrealistic. So I'll go overboard here and say we never know f or g. So some people might disagree with me on this, because there's kind of a field of nonlinear control called feedback linearization, where that's exactly what you do. You assume you know the nonlinear model, you cancel out all the nonlinearities, then you have a nice linear system. Everything works really well, theoretically. In practice, it's basically impossible to implement, because to know all the nonlinearities in your system is probably impossible. So you take a robot, you can spend a year perfectly modeling a robot, having a perfect robot model. All of a sudden the robot picks up the payload, your model's not valid anymore. So these kind of controls are much more practical if you assume you don't know f and g. But we can certainly have estimates of them. There's nothing wrong with that. So you can have f hat and g hat that you know, and you know they're not perfectly f and g. So step one would be to pick a positive definite control f of our function. That's kind of the first thing we're going to do. And then step two, so I call it a control Lyapunov function rather than a Lyapunov function, because we're going to make it negative definite, or try to make it negative definite. So step two would be take the time derivative. And step three would be to ensure d dot is less than 0 in some region. So there's two main possibilities. I'm going to say d dot less than 0 in some region. So you probably got the gist of this when we're doing all those stability theorems. In one case, you might have d dot less than 0 in some region D, and therefore it's uniformly asymptotically stable. Where should say for all x D. Where D includes the origin, so it's some ball maybe that includes the origin. So in that case, you get something that's uniformly asymptotically stable, and you get a region of attraction. Is my region of attraction D? Is that the same thing? It's the region of attraction D. Everyone remember? Remember from the notes. If the B dot is less than 0 with D, does that define our region of attraction or our region of attraction? Exactly. So if D is like a ball of radius r, then the region of attraction would be the ellipse that fits in with that ball, or even simpler, the ball that fits in the ellipse that fits in the ball, and you just get a ball, right? The only exception was the one-dimensional case. So if you are talking about the scalar case, there's no ball anymore, and then D region of attraction, the same thing. But usually you have more than one state, more than one input. B dot is less than 0 outside some ball of radius r. In that case, you get uniformly ultimately bounded signals. So these are the two kinds of basic possibilities that you find, and we have theorems for both of these. Okay. So if F doesn't equal F hat and or G does not equal G hat, then there's basically three possibilities for control designer. So one would be just to analyze stability. So maybe it doesn't matter. Maybe it doesn't matter that F isn't equal to F hat and G isn't equal to G hat. Maybe you get one of these things and it's fine. You don't actually have to do anything to fix it. You just might end up with a region of attraction or bounds that you might want to put some numbers on. So you might want to quantify what the stability characteristics are. But you don't necessarily have to go overboard trying to fix it. It might be okay. Two would be to make control robust. So you model uncertainty. So that would be especially true if the uncertainty is small. So you make some little fixed to your controller to make things robust to uncertainty. So that would be good if F was basically close to F hat and G is basically close to G hat. So there's just some little difference in there, and you can just make it robust to that difference. So that's what we're going to be doing in today's lecture. We're going to be looking at robust controls to make up these little differences. 3, make control adaptive. that's when you're talking about large uncertainties. So, if a robot arm picked up this pen here, I would probably make the control robust, because this pen really doesn't weigh much compared to a robot, so it wouldn't make a big difference, right? But if the robot was coming over here and picking up this chair, which I can't even do, that's going to be a huge change to the mass of the robot. That's when you would want to make it adaptive, because the chair is going to completely change the dynamics. You have to make it adaptive to basically make up for these large differences. Okay, so we'll do adaptive controls next week. Okay. Any questions so far? So that's kind of an overview of what we're going to do the next couple of weeks and why we're doing it. So hopefully that's okay. So let's talk about systems in canonical form. So the first equation I put up was a scalar case where you only have one state. So what if you have multiple states? Well, sometimes they're in canonical form, but it's not too bad. So sometimes systems look like this, and there's basically two ways of dealing with this system, which we're going to look at in the next few minutes. So method one is start with linear control. Use v equals x transpose px. So we looked at Lyapunov functions like that before. So we're going to basically apply the same methods we'd already learned in class. The second way to do it is what's called sliding modes. And this we don't know yet, so I'll teach this to you today. So those are your two possibilities. And basically, like I told you, like I encourage you to find a paper in the literature to do your project, because that's kind of the easiest way to do your project, is just to find some paper in the literature and kind of replicate the results, basically. So you will find both of these methods in the literature, so that's why I'm teaching them both to you, so that you can recognize them. So those are basically the two ways people do stuff. So almost certainly what you'll see will be in one of these two ways. Turns out the sliding modes is way more handy for us. It's way easier to design these robust controls, and especially these adaptive controls, using method number two. So I'll show you method number one, but for the rest of the course, I'm basically going to be using method number two. Okay, so let's do method number one first. So method one, I'm going to choose u equal to u linear plus u nonlinear, and u linear equals negative kx. And in this case, k is going to be a diagonal matrix of control gains with zeros on the off diagonal. These are all positive control gains. So if I do that, then I get x1 dot, x2 dot, all the way down to xn dot equals 0, 1, 0, 0, all the way to 0. This one I'll have 0, 0, 1, 0, all the way to 0. And then dot, dot, dot. And then on the last row, minus k1, g, minus k2, g, minus k3, g, all the way up to minus k and g times matrix here. Times x1, x2, all the way down to xn, plus 0, 0, and then 1 on the last row here, f of x plus g u nonlinear. So I get x dot equals ax plus b f of x plus g u nonlinear. So this matrix here is my matrix A. Does anyone recognize this at all? Any properties that this matrix has? Anyone remember what it's called? What kind of form is it in? What properties does it have? It's definitely controllable, but that's not what it's called. Close though, it starts with a C. I already wrote it on the board, so. That's it. Canonical, yeah. So this is what you call something in the matrix in canonical form in control systems. And we see something in canonical form with negative elements all on the last row. You know it's a stable system. The real part of the eigenvalues are negative, and so this matrix is basically like a stable matrix. So call this the stable linear part. In other words, the real part of the eigenvalues of A are less than 0. So in linear systems, that's good. It's stable. So basically, this is the part of the system we don't have to worry about. And then this is part of the system we now have to worry about as nonlinear control designers. Okay. You guys are lucky this board makes me go slow. So to understand this lecture, you might want to review your state space from your undergrad linear control systems for this to all kind of make good sense. So pick the control Lyapunov question. So if I call something a Lyapunov function, that means that v is positive definite and v dot is negative definite. But I haven't made v dot negative definite yet. So that's why it's called a control Lyapunov function, or sometimes a Lyapunov function candidate. Because it's not technically a Lyapunov function until you made v dot less than 0. So how did I calculate p? That's what I taught you in this course. So from this course, and remember how I calculated p? Or the command in MATLAB that does it? That'll be good enough.
Lab.
Yeah, lab. So lab is the command in MATLAB to do it. And it's solving the equation A transpose P plus P A equals negative Q. Remember? So you pick a positive definite Q, probably just the identity matrix, and then use that lab command in MATLAB to solve this equation, and that gives you P. So A was from that previous equation that I wrote on the board, right? So this works as long as A has, as long as the real part of the eigenvalues are negative, then this works. This is a valid Lyapunov function. Okay? V dot equals, remember I derived this formula in class. I give x transpose qx plus 2x transpose p b f of x plus g nonlinear. So at one point in your notes, that formula is derived, so I just use that formula from now on. Don't need to derive again. So if we know f and g exactly, which we don't, but if we did theoretically, u nonlinear, you can just pick as f of x over g. So it's not supposed to be g nonlinear, it's supposed to be u nonlinear. G times u nonlinear. Then v dot equals negative x transpose qx is negative definite. So then x would be asymptotically stable. So if we use u nonlinear equal to f hat over g hat, we have an estimate of f of g, then we get v dot equals negative x transpose qx plus 2x transpose p v f of x minus g f hat of x over g hat. So now it will result in kind of depends on what's in f of x. So I can't actually write like a general thing here. So is it uniformly asymptotically stable? Is it uniformly ultimately bounded? What's going on? So I kind of have to analyze a particular nonlinear function. I don't have any general statement I can make. I just know it's f of x. So it's going to be different if it's x squared or cos x or 1 over x. All those things are going to end up in different scenarios. Okay. Or a constant. So you kind of have to go case by case. Okay, so does that make sense so far? So let's look at doing the robot like this. And the robot dynamics I can write as x1 dot equals x2, mx1 x2 dot equals negative c x1 x2 times x2 minus b x2 plus u, and x1 is an Rn, x2 is an Rn, so it's an n-link robot. Okay. So I'm just going to do the simple case. I'm just going to make a control to keep things. For using this method, I don't want to get too advanced because things get tricky using this method. So let's keep it simple. I have some desired states that are just 0. In other words, I just want the robot to freeze and not go anywhere. So I'm just going to design like a regulating control just to illustrate this method. So I'm going to pick like some gains on the diagonal of k1, and some gains on the diagonal of K2. So just two diagonal matrices of gains. And then say U equals U nonlinear plus M x1 minus K x1 minus K2 x2. So you can see I'm doing things a little bit simple. I'm not going to the most complex case right away. I'm just going to assume I know M for this control, introduce this method. Things get complicated quite quickly when you don't know these things and you're just using estimates. So to illustrate this, I better take the simplest cases. So then I get x1 dot x2 dot equals 0, identity matrix minus k1 minus k2, x1 x2 plus 0, identity matrix times M inverse x1 minus c x1 x2 x2 minus d x2 plus u nonlinear. So I get x dot equals ax plus b m inverse minus cx2 minus dx2 plus un. So choose Q equal to I and solve A transpose P plus AP equals negative Q. Then I get D equals X transpose PX. Then I get B dot equals minus X transpose QX plus 2X transpose PB, just applying my formula again that I derived earlier in the course. So let's choose the U nonlinear to be Cx2 hat C hat x2 plus D hat x2 minus M hat x2. So then, if I had the perfect case where D hat was equal to D, C hat was equal to C, M hat was equal to M, then I would have E dot equals negative X transpose QX minus 2X transpose P B X2. So it's not particularly obvious that if this is negative definite, this Q is a positive definite matrix, probably identity matrix, so this is like negative definite term here. But this here is an X transpose, this is an X2. So you can't just say this is negative definite right off the bat. So probably we'll have to stick some numbers in here to analyze it. So that's kind of the thing you get with nonlinear systems. It's really hard to have like general formulas in nonlinear systems because usually visibility results depend on the very particular system you're doing and the particular form of the system you're doing. So let's do a particular system with some numbers in it then to analyze this. We'll see what we can do. So let's do an example. About one link robot, I guess you'd say, which would I guess actually be a pendulum. So in this case, X transpose P be X2 would be X1, X2, and P is just a symmetric matrix, so I'll just use 3 coefficients. This is just equal to X2B coefficient times X1 plus C X2. So I get B dot equals negative X1 squared minus X2 squared for my negative X transpose QX. So I get minus X2 B X1 minus CX2 squared. This one is supposed to be X2 squared. So this is looking more likely, right? So these terms are definitely negative definite, and then this one is just an X2 times an X1. So definitely looking like some good news here. So the way to attack something like this is to write it as a matrix and then see if the eigenvalues are negative. Rather than trying to, you could try to graph it or something. Looking at the eigenvalues is the easiest way to calculate them correctly. So if I was to do this as a matrix, and I want to make it a symmetric matrix so I can look at eigenvalues rather than singular values. That. K1 equals 1, K2 equals 1. Then my P I get from my Laplace equation. Did this before in class. We always end up getting this P. It gives you a B of 0.5 and a C of 1. The eigenvalues of -1, negative 0.5 over 2, negative 0.5 over 2, negative 1 minus 1 equals negative 2.05, negative 0.94. So that confirms that this is a negative definite function because the eigenvalues have negative real parts. So it's not necessarily super obvious looking at that, but we can confirm because the eigenvalues are negative. So that means B dot is negative definite, it's asymptotically stable. But that was assuming we knew all the model parameters, right? Which I'm saying is not necessarily a good idea. I just wanted to show you that how it works. So this is really, I mean, this is really no different than the examples I've given in class already, other than how it's a robot. But other than that, it's pretty similar to what I've done in lecture notes until this point. So there's really not much difference between this and previous lectures, other than this actual robot example. But the question is, what happens when the parameters aren't the same? So let's just pick one parameter, just to make things a little bit simpler, I'd say. But yeah, I should write down p dot is negative definite, therefore x equals 0 is uniformly asymptotically stable, right? So let's just look at the case that d hat does not equal b. So that's my friction term. So let's say my friction coefficient is off. That makes sense because friction changes every day depending on temperature, humidity, and how well you've oiled the machine, and how much the oil is drying up, and all kinds of other factors, right? So the chance that you're going to have a really good friction model is pretty slim because it's changing all the time. So it's very realistic that even in a well-modeled robot, you might not have the friction term modeled very well. So what if d hat doesn't equal b? Then you get b dot equals negative x transpose qx minus 2x transpose p b x2 minus 2x transpose p b m to the negative 1 minus d plus d hat x2. So analyze stability. So now you want to analyze the stability and find out if you have a region of attraction, or if it's uniformly ultimately bounded, or what's going on. So it looks to me, by inspection, that if I would say if d hat is greater than d, looks like they're going to be okay. So that would make this positive term, and have a negative sign here. And we already saw with an x and an x2, they ended up with something that's negative definite. So just eyeballing that, I'd say, oh, it looks like I just have to be a bit conservative. I think d hat a little bit bigger than the actual d, and it looks like it'll be uniformly asymptotically stable, right? But you have to go through the calculations and confirm that. You can just, graph it in MATLAB or whatever. That's symbolic math, something. So you figure out some way to analyze where, find out where b dot is less than 0, basically. And, we already know this term is okay because we just analyzed the effects of that term previously with those numbers. But then it'd be up to this term. So things can get kind of complicated using that method. And it's not obvious how you would make this robust or adaptive or anything. So it's not real obvious how I would redesign U to make this robust to changes or to differences between D and D hat. It can be done. So you'll find papers in the literature that do it. It just gets complicated, that's all. So it's not real nice to work with. So I don't like to use this method. Like I said, you might find papers in the literature that use it. So at least now you'll understand what they're doing and why they're doing it. So for us, for this course, we'll stick with the sliding mode method. So I'm not going to show this method again. This is kind of awkward to work with. And I'll stick with the sliding mode method. And the sliding mode method is much easier to make robust and adaptive. Okay. Any questions about this method? All right. Okay. So like I said, it's not really any different than what I've been doing in the lecture so far to this point is a more complicated example. So method 2. Sliding modes. So remember, we're talking about methods for dealing with systems in canonical form. Right? So the first thing you do is you define sliding mode. Or sliding surface, or auxiliary error, whatever you want to call it. There's a bunch of different names for it. So basically adding all these states together. So the idea here is if we define the sliding mode, what we can do is we can just force Z to 0. That's all we have to worry about is forcing Z to 0. We don't have to worry about forcing each one of these individual states to 0. So the reason is that when Z is equal to 0, then I have system xn minus 1 dot equals xn equals minus a1 x1 minus a2 xn2 minus dot 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 all the way down to an minus 1 x n minus 1. So I'm just rearranging this equation with z being set to 0. So what kind of system is this? I just wrote down here. And it's an awful lot like the last one, I guess.
So exponentially decreasing then?
Yeah, exponentially stable linear system, right? So I have, this was, we're talking about a system with so if we're talking about, if we're talking about system that's going to have all negative eigenvalues, you did like this, these would be like the poles in a transfer function, right? They would all be in the left-hand plane. They're all negative numbers. It's an exponentially stable linear system. So it's exactly the way you want to see a system written, know that it's doing exactly what you want it to do. It's in this form, right? So that's kind of what you want to see for a canonical system. And so as long as we make z go to 0, we'll get that. So the idea is that first, so this is a stable linear system. Called the sliding surface. So that's kind of what we want. So what we do is we design all we have to do is design the control to make sure z goes to 0. So design a control to ensure force system to the sliding surface. I.e., make z go to 0. So after it's on the sliding surface, goes to 0, since it is exponentially stable. So the way this is usually drawn, you have like x1 and x2, and you have x1 dot equals x2. So if x1 dot equals x2, and it's actually on the line like this, where x1 equals x2, then that's the sliding surface. So the idea is
x1 equals to x2, or x1 equals minus x2.
Or sorry, x1 equals minus x, yeah. And then the idea is to go onto the sliding surface. So if your system starts here, the idea is to design a control, a nonlinear control, to force you to the sliding surface. And then once you're on the sliding surface, you just stay on the sliding surface and go down to 0. So that's kind of the general, that's just kind of the general idea. Make sense? So this is x2 equals negative x1. This sliding surface. So in this case, my control alpha function is b equals 1/2 z squared. Okay, so you can see why this is easier already. The last one I had e equals 1/2 x transpose px. Straight away is like a vector matrix equation, right? So let's get complicated real fast. This is actually much simpler for designing robust and adaptive controls, basically because it's a scalar equation. So it's actually much easier to work with. So e dot is equal to z dot. E dot is equal to z a1 x2 plus a2 x3 plus all the way up to a(n minus 1 xn plus f of x plus gu. So this part here is just xn dot. So just subbed in xn dot f of x plus gu. So for my control design, I can choose u equal 1 over g hat minus a1 x2 minus a2 x3 all the way up to minus a and minus 1 xn minus f hat of x. And I better throw in a little feedback term there, linear feedback term minus kz, where k is a positive control gain. So then, if I had the case where I knew the model exactly, so I had f hat equal f and g hat equal g, then I have v dot is equal to minus k z squared. It is negative definite, therefore x equals 0 is uniformly asymptotically stable. I should say z equals 0 is uniformly asymptotically stable. So I'll eventually get to z equals 0, and that will drive x to 0. So I'll be on the sliding surface. So let's take the case now where we don't have this perfect model knowledge, which is, like I said, pretty unrealistic in real life. So let's take the case where f hat does not equal f, but we know d max such that, so we kind of take a look to see how close f hat is to f. So this is supposed to be like the worst case scenario. So let's say, looking at the very worst case scenario, I'm pretty sure that f minus f hat will be less than this d max in some region d, right? So I can probably establish that pretty easily if I have some idea of my nonlinearity of my system. The most they can be, the less they can be, that kind of thing. So I have an idea, I probably have an idea of how close I can get. Then use sliding mode control with a discontinuous term. Okay, so I'm going to apply u equal 1 over g hat minus a1 x2 minus a2 x3 minus all the way to an minus 1 xn minus f hat minus kz minus d max times the sine of z. Okay, so the sine of z, literally if z is positive, it's 1, z is negative, it's negative 1. Technically, if z is 0, sine z should be 0. But that's a bit of a mathematical technicality. You really have to remember that in real life. So, we'll still keep the case where g hat equals g, because if g hat doesn't equal g, it gets a little more complicated. So let's keep things simple for now. So we get minus kz squared plus z times f minus f hat minus d max times the sine of z. So E dot is less than or equal to minus kz squared. In other words, this term always is bigger or equal to this term in magnitude. But because this has a negative sign, whoops, I missed the z there. Sorry, z sine z. So z sine z will be negative. Yeah.
So sliding mode control is always used on the system that until the last states, and the states are something like that is 1 dot is equal to x2, x2 dot equals to x3, and n minus 1 dot is equal to x1.
That's right.
There's like
Canonical form.
Yeah.
Yeah.
So there's regions what we cannot use sliding mode because it's not.
It's in the canonical form, yeah, it is.
Because the x1 dot is
Flex too.
and x2 dot is something like this.
Yeah.
It's not x1, x3.
Right, okay, yeah, I see what you mean. For the flexible joint robot, yeah, we're gonna learn, yeah, so this is for the rigid robot, that's right.
Yeah.
For the flexible joint robot, we'll have to do backstep.
Yeah.
So it's a little bit different. This, yeah, you're right, just finding canonical form. So, yeah, we're gonna do backstepping in a couple weeks. So, basically, I'm showing you a bunch of techniques for rigid robots, and then I'm gonna show you this magical technique called backstepping, and then all of a sudden, you'll be able to take everything I showed you for rigid robots and apply it for flexible robots. So everything we're learning here for rigid robots is totally applicable.
Backstepping, basically putting the flexible robot into canonical form.
Not exactly. In backstepping, you're designing a desired, because we have a spring at the joint. So you're treating that spring like a control force. So you're designing like a desired deflection of that spring to give you the right torque to control the robot, and then you have to go back and then make sure the motors are giving you the right torque to make that elastic deflection that you want in the joint. But we'll get into that in a couple weeks. So this is negative definite. Therefore, z equals 0 is uniformly asymptotically stable. Now you do have to worry about discontinuities mathematically. So this is a discontinuity here. Sine z, it jumps between 1 and negative 1. D dot is not supposed to be discontinuous in Lyapunov theorems, but if you notice, this gets multiplied by z here. So this part is discontinuous, but it switches at 0, and z brings it to 0 at 0. So it doesn't end up being discontinuous, right? It ends up being like negative z sine z would look like that, right? So it's not discontinuous. But, so you do have to worry about discontinuous terms, but as long as it's multiplied by z and the sine of z, it's not actually discontinuous. But another reason you have to worry about discontinuous controls is that they can be bad in real life. So they can cause chatter. So if you did it in a robot and you had Dmax too high, so if Dmax is kind of small, then you can get away with another robot. But if Dmax became rather large, you create this large chattering control force, and it would actually cause the robot to vibrate. Nobody really likes a vibrating robot. So it's okay for robotics up to a point, but after you start to introduce this vibration, it's no good anymore. So it's only useful for really as long as Dmax is really small, it'd be okay. But if Dmax was large, like if you're trying to make Dmax to be robust, so if you pick up this chair, like it just wouldn't work. You have way too much vibration.
So you can use it only on robots, not adaptive, right?
For the sine z, yeah. This is a robust control. This isn't adaptive at all. And then the other bad thing is that don't apply this in a process control. So if you try to apply a signal like this to a valve in a process control, then you just wreck the valve. Everybody's mad at you. So it's okay for like electric motors, because electric motors have discontinuous signals put into them anyway. I mean, mostly you usually put a pulse width modulation PWM signal into an electric motor, so that's discontinuous. So electric motors don't care if you give them discontinuous signals, so it's not going to wreck the electric motor. But in more broad sense of control systems, it's not necessarily good to have a discontinuous signal, depending on what your actuator is. So if your actuator isn't an electric motor, think carefully about whether you're going to wreck your actuator with such a signal. Okay, so these kind of things can be handy, probably mostly just for electric motors, and if Dmax is small, you can probably get away with it. It's nice because it makes things uniformly asymptotically stable rather than bounded, which is kind of a nice result. So let's do the example for a robot. We have time to do this before. Well, let's take a 5-minute break. So I don't want to take you past 8 o'clock today, so we'll just take a quick bathroom break and be back here in 5 minutes, and then I'll try and finish off before 8 o'clock, so we're not here till late at night. So let's reconvene in 5 minutes.